Now let's take a look at how to assess for an association between two variables when the assumptions associated with the linearity normality-based methods are not warranted. So here I have the number of samples tested in 2011 and the number of percentage resistant samples in 2011. We can go and do a distribution on both of these variables. And if you recall, the number tested was a skewed variable that is not normally distributed. And if we look at the normal quantile plot for both of them, while we see normality is warranted for the percent resistant, it's definitely not warranted for the number tested. We're also dealing with borderline small samples here. And in addition, they have to be bivariately normally distributed. So with one of the variables being not normally distributed, it's unlikely, though possible, that they are bivariately normally distributed. So let's jump in and look at testing these assumptions and then seeing how we can compare whether or not the number of samples tested is related to the number or percent that are resistant in the same year. Go to Analyze, Fit Y by X, and we'll put our percent resistant as our Y and our number tested as our X. It seems to me to make more sense to see if the number tested predicts the number or the percentage that are resistant, since the testing happens before the percentage resistant results come back. So I'll press OK here. And right off the bat, you can actually see that the plot looks a little strange. The scatter plot looks a little strange. Most of our values are centered here at less than maybe 300, whereas we've got these three outliers all the way out here. And the concept of maybe a line fitting here seems like it might be a little flat, and that maybe these three would be really running that line. Essentially, it looks like it's predicting relatively flat through this middle part here and then trending down towards where these three leverage or outlier points are. So before we actually look at any of the linear fit, let's go ahead and look at our residual plots here. So the first thing that I want to look at is this predicted by the residual by predicted plot. Recall we talked about the homogeneity of variance and the patterns. We can see a very clear pattern here in our residuals, that it's very narrow on the left side and very wide on the right side, that the spread of variability above and below as we go this way to the right on the x-axis is not the same. We have three very strong outlying observations. If you could make a case for determining if those observations are incorrect, then perhaps you could delete them. If they are very unlikely, then perhaps you could delete them and try refitting it. But removing outliers is a dangerous business. Sometimes those outliers are the most important part of your data, so do not remove them unless you can really justify it. In this case, these are reasonable values. They are real values, and since we see this pattern in our residual plot, we don't want to use a normality-based method. So the fit Y by X here option that we have would also be to fit the density ellipse to see if we can take a better look at normality. And again, we can't even get the whole density ellipse into the plot. We'd have to go way to the left of 0 values tested, and that's not even a real value. So I think we're sort of coming to the conclusion here that this normality-based or linearity-based methods are not what we would need to assess this relationship. In JMP to do that, you go to Analyze, Multivariate Methods, Multivariate, and we'll simply enter in both of our columns that we want to compare and press OK. And what comes up first is the Pearson's correlation, so the large sample-based correlation. We don't want that. We actually want the Spearman's. So under the red arrow, we'll go to non-parametric correlations and ask for Spearman's. And then at the bottom here, what you have is the correlation that can be interpreted in the same manner as a Pearson's, only it's based solely on the ranks of the data. And you may say, what are the ranks? Well, the ranks actually just take your response values and put them in order, lowest to highest. And then they're actually doing a Pearson's on the ranks. So we could actually do our distribution here for the number tested and the percent resistant and press OK. And then we could ask for our distribution to save the ranks. And it will save the ranks for both of our values. So you can see here for Alabama, the number tested was 143, and that's actually the 24th value. The number tested for California was 1,528, and it's the 42nd largest value. It's actually the largest value we have. Whereas the number percent resistant is 17. If we actually do a fit Y by X with our percent resistant ranked as our Y and our number tested rank as our X and press OK, you can see now that we have a more evenly distributed scatter plot. So it's really just looking at the ranks of the values. And from there, I could ask for the density ellipse. I could ask for, then from the density ellipse, our correlation. And you could see that our correlation on our ranks is very similar to the Spearman's correlation here. So our correlation on our ranks is minus 0.11, and the Spearman's rank correlation is minus 0.11. Neither one of them are statistically significant. Now, different programs will deal with ties and ranks in different ways, so you may end up with slightly different values depending upon the way that they deal with the tied ranks. But it's sort of the math behind that's not really important. And simply if you report the Spearman's row, as long as you don't have a lot of ties in your data, then you should be just fine with the conclusions that you draw. In this case, we would draw the conclusion that the number of samples tested is not associated with the percentage of those samples that are antibiotic resistant. But we do not have a linear equation. We do not have prediction. All we can say is that there is no association between higher numbers tested and higher percentages resistant. So that's how you get a Spearman's correlation. It's somewhat limited in the interpretation, but it does allow you to assess the question of a relationship between two variables when they are either not linear and or not normal and or do not have homogeneous variances.